Greetings everybody, and welcome to the latest edition of the Physics Corner. This is a video series in which we show how to set up and solve introductory physics problems. I am your host, Dr. Christopher Sorolla. Today we're taking a look at a very famous case in physics, in electricity specifically, on what are called parallel plates. Now, parallel plates, in this case, we will have charges on opposite sides or opposite plates. And to kind of illustrate that picture-wise, let me sketch what we really mean here. So imagine we're looking at a side view, by the way, of such plates. So imagine we have two plates that look like this. We'll have positive charges on the left-hand side and an equal number of negative charges on the right-hand side. So a couple things about this. First, these are just to show one side's positive, one's negative. And then the left-hand side will have a total of a positive capital Q of charge, and the right-hand side, a total of a negative Q of charge like that. So the actual number of charges we're going to determine, that's part of our problem today. Now, just to say it, because the rules that you've learned for drawing electric fields are this: field lines may not cross each other. Field lines must always go from positive to negative. So what that means is, between the plates, the field lines essentially are parallel and look something like this. So you'll have an electric field between the plates like that. And that's what we want to find today. So, given some numbers, we want to find or determine what is the electric field between the plates, what are the number of charges on each side, and while we're at it, let's go ahead and determine the voltage of between the plates. So, let's get started. So, we're going to return to an old style way of doing things here. Let's set up some knowns and unknowns. So, known and unknown quantities. This will help because this is introductory days here for you folks in electricity, so let's do this. So what do we know? It says here the parallel plates are separated by 1 centimeter in vacuum. Let's call that distance d, and let's change everything to metric or to standard units. So 1 centimeter is 0.010 meters. Okay. The plates have a surface area of 25 square centimeters, and again, let's change that to square meters. Now notice how this works. This is something to be aware of. There's 100 centimeters per meter, right? And so there's a temptation just to divide the 25 by 100, but it's not centimeters, it's centimeters squared. So you have to divide by 100 twice. If you divide by 100 once, you get 0.25. So this is how we get the 0.0025. That's why we have that way. Here's something else that's going to come up a lot for us. Each of the plates have 5 NC of charge. What is the N? What's the C? Well, C stands for coulombs. That's the standard unit of charge. The N is 10 to the minus 9, and there's a prefix called nano, N-A-N-O. So the amount of charge is 5 times 10 to the negative 9th coulombs, and looks like that. So that's an important thing to have. Now, one more item, or a couple more items, excuse me. It says that the plates are separated by vacuum. There's an idea called the dielectric constant, which will come up a little bit later on. We're going to introduce it here, even though we probably won't end up using it explicitly. But the dielectric constant is basically a measure of insulation between the plates, if you will. By definition, if you have vacuum, you have no special insulation, and that constant is exactly equal to 1. Now, should we decide in a future episode to put a material between it, like say, rubber or plastic or wood or paper, something like that, we'll actually have to assign a number to it, and that number would be larger than 1, because it means that it is doing an insulating job. Vacuum is actually a pretty good insulator in a sense, and so it's not a bad thought to have it there, but we're going to leave it like that for simplicity's sake for today's episode. So we're just mentioning it here. We're not going to explicitly use it as such, but it's something that'll come back that we need to deal with if we go further with this in future episodes. Last thing that's going to come up is something called the permittivity of free space. And specifically, this isn't a vacuum. That's why we talked about this a little bit. Epsilon naught here, or E naught, if you will. Vacuum's version of this. And this is a little bit of a complicated looking number, and a very tiny one on top of that. And the units look like that. So where does this come from? This is related to the little letter K constant that you've talked about in previous or different circumstances. But whereas K was really, really large, epsilon naught is very, very tiny. One way to think of this, it's not the only way, is that K represents the relative strength of electricity as a force of nature. So the number is a very big number. Or epsilon naught, the permittivity, how well space permits electric fields to travel. It's very easy for electric fields to travel through vacuum, therefore the number is very small. And that's one way to sort of consider what that means, if you will. All right, so those are all those kinds of things. Now, unknown are the number of electrons. I'll call it capital N for short. The electric field between the plates, that's capital E. And the potential difference, or voltage if you prefer, is delta V, and looks like that. So those are our knowns and unknowns, and a picture to go along with it to illustrate what's happening. Okay, so let's do the easy one first. Let's do the number of charges in each plate. Now, in this particular case, we're interested in the electric field between the plates. So it's not, in this case, the idea that you would sum up the total charges and come up with 0. If you did that, of course, there's nothing to talk about, right? The whole point is that we have the charges separated. They're kept separate. They're not going to allowed to touch each other, not allowed to meet. And there's a positive amount of charge on the left and a negative amount of charge on the right. And that creates an electric field between them. So we do need to actually use this number of charges when we calculate the electric field that we're going to calculate later. And that means we need to know how many charges we have, or it will at least be illustrative to have a number of charges. How much or how many charges are involved in 5 nanocoulombs of charge? That's kind of an interesting question. So there's one more number where it's unknown that we can look up. And that's the charge on of an individual electron or proton. And that is 1.6 times 10 to the minus 19th coulombs. All right. Now, if it's an actual electron, of course, that's a negative number. If it's a proton or the absence of an electron, we'd say that's a positive number. We're not interested in that for just counting up the number. It doesn't matter whether it's negative or positive in that case. So I'm going to put a negative sign in parentheses there to remind us that the actual electron has a negative charge on it. But I've got in parentheses because that's not relevant to the question we're going to ask about it. So in any case, part A then. So let's get to solving. So what is the number of charges? Now, this is a simple question, perhaps, but this is why we're doing these videos, is to show you why they might be simple or give you some thoughts on how to approach this. So let's suppose I were to ask you a separate question, something that you would be able to answer more easily, perhaps. How many pennies or cents are there in a dollar? And you'll say, oh, there's 100 cents per dollar, right? How many pennies are worth a $10 bill? And you say, oh, that's 1,000. Well, how did you get that? You look at how much a penny is worth. A penny is worth $0.01, if you will. And you take the total amount of money you have, say $10, and divide it by how much an individual penny is worth. 10 divided by 0.01 would give you 1,000. So 1,000 pennies are equivalent to $10, right? Which is a hint. If you want the number of something, we want the total amount of whatever it is we're talking about. In this case, the total amount of charge divided by what each individual charge is worth. Looks like that. So here's a way to say this. So we have 5 times 10 to the minus 9th coulombs here. An individual electron or proton is worth 1.6 times 10 to the minus 19th coulombs per charge, if you will. I'll write out the word to make it real obvious where we're going with that. And just to make things a little simple on ourselves, I'm going to round off to the nearest, say, 2 digits just to keep it light. And if we do that, we get 3.1 times 10 to the 10th charges. Or, if you prefer to write it out in words, 31 billion charges. And we get that. So, what is that really saying to us? What it's saying is that even a small amount of charge actually represents an enormous number of individual charges. Okay. Now, to back up a little bit, the things that actually do the work in electricity, if you will, that do all the activities, are almost always, not always, but almost always electrons. Why is that the case? Electrons are in the outskirts of atoms, and they're easy to tear off of atoms and make them do things. Electrons are also very light in comparison to their cousins, the protons and the neutrons that atoms possess. Something like 1,800 times easier mass-wise to move around. And for those variety of reasons, electrons are typically the things that matter. Each electron has the same amount of charge. One electron looks exactly like another electron in that sense. And therefore, if we just want the total number of electrons, we can do this kind of calculation. Okay. So, with any case, this is more of an aside, if you will, calculation. We could just ask this question for any time we had this number of charges, right? It didn't have to be parallel plates. But it's sort of worth remembering or knowing how many charges are actually present when we do calculations like this. And it turns out the number's decently large, right? Even a small amount of charge, nanocoulombs, requires a lot of charges. Okay. All right, on to the next part. So the part that's a little bit more important for this question, a little more to the point of the parallel plates, is the electric field. So an electric field, we can get this in a variety of different ways. Here's one way to do it. Electric field is defined by something, or can be talked about by something called Gauss's law of electricity. And Gauss's law of electricity says this: the electric field multiplied by the area equals the charge that's inside this section that we're talking about divided by, this permittivity constant. Okay, now we're using vacuum, so E naught is perfectly legit here. So this is Gauss's law for electricity. Now, in order to apply Gauss's law, you need a decent amount of symmetry. What do we talk about here? Well, let's imagine, for example, we were to sketch, say, a little pattern like this right here. And then ask, what's the amount of charges passing through this in this volume of space? Oh, there's the positive charges, okay? And what's the area? It's the surface area of the plate itself, right? So we can calculate the electric field that is given off by that plate, or that's associated with that plate. And we could do a similar calculation for this section over here if you prefer as well. Now, I'm not going to get into the depths of that. For this, it's enough for us to know that this works for these purposes, but this is the conclusion we get. Which is to say, the strength of the electric field between the plates then is the charge multiplied by area over epsilon naught, like that. Or excuse me, not to multiply by area, divided by area. I'm sorry. Make sure we say that correctly. All right, not sure why I wrote that up there. Brain freeze. So, some other way to describe this, by the way, and I'm going to write this, but I'm not going to use it to calculate with. You can describe it in this fashion. So if you ever see this version of it, this little letter sigma here for electricity purposes means surface charge density. How many charges are in a certain area, space? That comes in handy in a lot of calculations. We are not given it that way specifically, but there are a lot of problems in which this happens, and so if you encounter it in other places, that's just what it is. It's a shorthand for that. But we don't have to do shorthand because we already have these. So we're going to calculate it straight up. So electric field is the total amount of charge. Again, 5 times 10 to the minus 9th coulombs. The area, we said before, is 0.0025 square meters. So that doesn't sound like a lot of square meters, right? I mean, because, well, let's think about it. 1 meter is 100 centimeters, right? So even a lot of square centimeters ends up being very small in terms of square meters, right? So that's how that works like that. And epsilon naught, again, is this funky looking fellow of a number, 8.854 times 10 to the minus 12th. Then coulomb squared per Newton meter squared is the actual set of units that is associated with that, right? So if you've got your calculators out, it's time to do some calculating. I'll let you do that for a moment. And I'm back. It's the magic of pausing videos when you want to. And the number we come up with is roughly 230,000 newtons per coulomb, okay? Or if you prefer to write it this way, 2.3 times 10 to the 5th newtons per coulomb. Now, I'm going to also do a little bit of a cheat here looking forward a bit. In this case, it's not just this way to write it, newtons per coulomb, and that's correct, by the way. That's a perfectly legit way to write an electric field. But also there's another interesting way to write it in terms of units. We could also call it volts per meter. Newtons per coulomb, volts per meter, same thing. And the reason that's important is because it's a hint as to how to get the next step, the voltage, or the potential difference between the plates. Let's go ahead and do that one next. Okay, we're back. And I redrew our picture here with one interesting small difference. So we still have positive charges on the left plate, negative charges on the right side plate. There's still a parallel electric field that goes from one side to the other. But now I've added D. What's D? D is the distance between the plates. Now, in this particular case, we're going to do something a slight bit different, just to mention it, than we've done before. In this case, we're measuring actually from surface of this plate to surface of this plate. Now, often in the past, we'd measure from, say, the center of something to the center of something else. But here we're measuring from surface to surface. Why? These two plates are conductors. And something else that you've probably seen already is that when charges are placed on a conductor, they spread out as far away from each other as possible, which means they will end up on the surface. So the charges are not at the center of the plates, they're on the surfaces of the plates. That's why we're using the distance between the surfaces. It's a really minor point usually for these kinds of calculations, but it does exist. So, if you see that, that's what's happening. So, we had determined the strength of the electric field was rounded off 2.3 times 10 to the 5th volts per meter, like that. Okay, so there's a couple of different ways to get the potential difference, but here's an interesting one. Another way to define an electric field, and again, I'm going to put the negative sign in parentheses because we're not concerned with its application otherwise. Just want to mention that it does exist in other places. We'd have to worry about it. The electric field for cases like this should be a delta X. Sorry, looks like that. Electric field is the change of voltage or potential difference over a displacement. Remember delta X from physics 1. Delta X represents displacement, a change of position. What kind of change of position are we talking about here? We're talking about from here to here. This distance D is what we're talking about. And this is something else, by the way, that has to be done. Whenever you work with potential difference, there must be a difference of position. This is inherent in the definition of what voltage or potential difference is all about. You can't have a sensible answer or an answer that works at all for a case where you say measure at the same location. Okay? In order to have a potential difference, there must be a difference of position. So delta X there, all right? We're not concerned with the negative sign for my purposes here, so I'm not going to worry about that. But what this means is I can turn this around, and delta V then is equal to E delta X, or as it's called in most problems of this type, E times D. All right, this makes for a simple calculation then. Electric field was 2.3 times 10 to the 5th volts per meter. The distance was 1 centimeter or 0.01 meters. And now it's a little bit maybe perhaps easier to see why I decided to go with volts per meter for the units for electric field. I did that because then meters cancel and we get volts. 2.3 times 10 to the positive third volts, or if you prefer, 2300 volts. And that would be our answer for the potential difference. Okay. So, it sounds like we have a lot going on here. Now, there's a lot of charges, but the electric field was, pretty large too. The amount of charge was small, but lots of charges, very high electric field, and a sizable potential difference. Okay. So it looks like there's a lot going on. We're going to leave it here for today. At some point in the future, you will get to a different place in your education here for electricity, and you'll encounter the parallel plate situation again. But we're going to hold off on that and do that in a different video. All right, everybody. Technical assistance for these series of videos comes from our good friends Sidney Gautraw and Sophia Turner. Funding for these programs is from the University of Mississippi and the University of Southern Mississippi. We film these videos in Hattiesburg, Mississippi. I am your host, Dr. Christopher Sorolla. Thank you, everybody, for your attention, and clear skies.